That's actually something which you're going to study next year or next semester with Ursula Walter, that there are some situations where a company might be willing to do projects which have negative net present values. It's a weird situation, but the reason for this is that the equity holders and the debt holders might have conflicts of interest. So the equity holders, the managers, would like to do something with the objective of hurting the debt holders. Right? So you do something that's overall destroying value, but on the other hand, you can steal something from the debt holders. Right? And if the amount of money that you steal from the debt holders is larger than the loss in value of the company, you would be willing to do that. So generally speaking, that's every investment that increases risk is kind of beneficial or kind of susceptible to these kind of behaviors. Right? So when you study kind of problems from asymmetric information and principal agent problems next semester, that will be exactly what you will be looking for. Kind of inefficient, non-optimal, inefficient behavior, that means negative net present value, that can be optimal for equity holders. And it's a so-called asset substitution problem. Okay, so let me look for time. Yeah, so let's see if there are any questions. So that was kind of a very, very quick rundown through something that we do kind of over multiple lectures in the bachelor. But I hope that you've seen this before, and remember there's very good literature where you could look this up if you need to have more details. Okay, so I mentioned that I want to let you do a little homework assignment, and that requires a formula, which is a simplification of the formula that we've just seen. And that is the so-called Gordon's growth formula. So this is a simplified formula that you can apply on a very special stream of cash flows. So let me first tell you how the stream of cash flows looks like. So the first thing is that the cash flow goes on until infinity, so it's basically never stopping. The first payment that you have is after 1 year. So let's do the first few years here. And the first payment that you will get can be a risky cash flow. So that would be the expected cash flow that you get after 1 year. It's important that at time 0 there's also 0. And now this cash flow that you get after the first year is growing with a certain percentage every year. And this growth rate is going to be constant. So the next year you get an expected cash flow of x multiplied with 1 plus the growth rate. I mean, the growth rate is constant, you could take that out of the expectation operator, doesn't really matter. Right, so your expected payment is growing every period by the same rate. And then the next year you would get an expected cash flow of the same starting value x multiplied with 1 plus g, but now squared because it's growing for 2 years. There is a special case, again, of this cash flow, which is called the perpetuity. So if you have a growth rate of 0, it means that the cash flows will be the same in every year. That's what we call a perpetuity. In German, you would call this here ewige Rente. That's the perpetuity. Start off with a certain cash flow, x, and then it's growing every period by the growth rate, g. We have a constant discount rate r that we can use, which is risk adjusted already. And the risk every year now is the same, right? So the risk's not changing in any shape or form. So how do we compute the present value? Well, we would take every cash flow here, the first cash flow discount for 1 year, take the second cash flow, discount for 2 years, and we take the third cash flow, discount for 3 years, and so on, And we would do that with every payment until infinity. It's a very, very lengthy kind of series. Now it turns out that that equation has a very simple solution. You can calculate the exact value by taking the expected value of the first cash flow and divide by the discount rate minus the growth rate. That's the correct solution, or the shortcut formula for this stream of cash flows. Coming back to the perpetuity was g equal to 0, right? So if you plug in g equal to 0 here, your shortcut formula for the perpetuity would be your expected cash flow divided by the discount rate. This is the perpetuity formula. So that would be here. The present value of the perpetuity is expected cash flow divided by the discount rate. Now, these streams of cash flows are not realistic because they're infinitely long, but there might be appropriate simplifications in some instances, and I'm going to show you one example in a second. Again, researchers like easy things and easy solutions, so we're most often using this if we're interested in kind of shortcutting this computations a little bit, but making it somewhat realistic. There are actually some very few financial products that work like this. I mean, something that is like a perpetuity is a so-called console bond, that it's a bond with infinite lifetime. The British government has a couple of these bonds, and the reason, basically, it was the other way around. So the formula was there first, and then they said, okay, let's invent a financial product where we can use the formula for. Right? And that was the birth of the console bond. And it's very easy to kind of compute the value of it. You just look at what is my coupon that I get from the bond every period, which divide by the discount rate, and you're done. Right? It's very simple, very straightforward. Yeah. So this will be something that we sometimes have in problem sets, but I'm going to show you kind of, I think, somewhat realistic application for the growth formula in a second. Again, that was the thing that I'd like you to do as a homework. Before we move on, do we have any questions regarding the general structure of the cash flow and the solution? Okay, so maybe let's first tackle a problem, and then I would like to see if we have the time for it today. Yeah, I would like to show you a brief derivation of the formula that you should see where this comes from, because it's actually quite simple to do. But let's first do a special case. And the special case is, what is the result of the formula when the discount rate and the growth rate are the same? So look at the formula in this specific example. That would be 1.1 divided by 10% minus 10%. So 1.1 divided by 0. What do we do?
Doesn't make sense.
Yes, it doesn't make sense. So you could even have a scenario where the growth rate is larger than the discount rate, and the result would be negative then, right? Because we divide by a negative number. That also doesn't make sense, by the way, right? So negative results are bad. But can someone maybe see what is the correct result in this case here, when the growth rate is equal to the discount rate?
Maybe the result is infinity, so we can do it like infinity.
That's actually the correct solution. So that stream of cash flow is so valuable that it actually reaches infinity. Right? There is no finite price that you could kind of write down for it. I could have asked differently. The question is, do you want to have such a cash flow that starts off with 1.1 and grows at a rate of 10%? Right? You would immediately see, it's okay, every year I get more and more and more. That sounds interesting, right? So you should be willing to pay a decent price for it. Right? It's definitely not 0, right? So dividing by 0 is not allowed anyways, but 0 or negative numbers are definitely wrong. How can you get to this solution? Well, yes, there is a shortcut formula, but still the first part of the formula is always correct, right? So maybe let's just use the first part of the formula. and write this down. So I've chosen the numbers such that we get an easy result. So in the first period, we get a 1.1, and we have to discount at 10%, right? In the second period, well, we get 1.1, and now this is growing at a rate of 10%. And now we discount at 1 plus 10%, however, for 2 years, right? So you square this.